This video is a hands-on guide to exploring and interacting with your application's traces using Grafana Alloy, empowering you to build efficient and end-to-end observability workflows. Hello everyone, my name is Mohammed and welcome to CodeOps by Mo, my YouTube channel. This is the third video of Grafana Alloy playlist, okay? Until now, we learned how to work with logs and metrics using Alloy, and now it's time to work with traces, okay? Um, in this video, I'm going to implement a tracing pipeline where we are going to receive the traces of our application, to process the traces, and to send those traces to a backend like Grafana Temple. And we do that through Grafana Alloy. It's very amazing. But before implementing this tracing pipeline, I prefer to explain some different concepts for the viewers who don't know these concepts, like what is trace, what is span, what is instrumentation, auto-instrumentation, manual instrumentation, okay? And after that, we will implement our amazing tracing pipeline using Grafana Alloy, okay? So let's explain these concepts. I think this is a good example to understand how traces and spans work, okay? If you pay attention here, a trace shows a full path a request takes as it moves through different parts of a system, like going from one service to another in a microservice or container-based application, okay? And traces help you see where slowdowns or problems might be happening. And here, each trace is made up of smaller parts called spans, okay? And a span represents one step or action in the journey. And it includes when the step started, how long it took, what operation or task it was doing, for example, like calling an API or accessing a database. Okay. And spans are usually connected. Okay, one span lead to the next, kind of like a family tree, unless it's the very first one called the root span. And spans are include useful details like the HTTP method, the service name, and other related info. Another concept that is very important is instrumentation. Instrumentation means adding special code or tools to your application so you can collect data about how it behaves, like how long something takes, where it fails, or how services talk to each other. It's like installing sensors in a car to see how fast it's going, how much fuel it's using, or when something breaks. Okay. And we have two different types of instrumentation. Okay. The first one is manual instrumentation, and another one is automatic instrumentation. But what is automatic instrumentation? These are tools automatically add tracking code to your app without you needing to write much or any code. For example, you install an agent or library like OpenTelemetry, and it automatically tracks things like the HTTP requests or database calls. And it's good for fast setup and basic visibility. For example, here we can use different auto instrumentation frameworks based on your programming language, like Java, .NET, Python, and Go. And you can add instrumentation points to your application through auto instrumentation frameworks. Okay. And another type of instrumentation is manual instrumentation. It means that you write the tracking code yourself. For example, you manually create a span around a specific function or piece of logic to measure how long it takes or if it fails. And it's good for custom or critical parts of your app that automatic tools don't cover. So I think it's good to use both of them in our application. Okay. And another concept you need to know is tracing pipelines. It's very important to know that what is a tracing pipeline before implementing it. Okay. A tracing pipeline is like a factory line for your trace data. Okay. If you pay attention here, it takes in trace info from your app, process it, and send it somewhere useful, like a backend. Okay. And it's made up of building blocks that each do a specific job. For example, the first one is a receiver. These are the entry points. They receive trace data from your app or agents. Okay. And a receiver might accept data in formats like OTLP, Jaeger, or Zipkin. It depends on you to use one of them. And another component here is processor. They clean up or enhance the trace data. We have different types of processors. For example, we can modify our trace data. We can add a resource and a span attributes to our trace data, and so on. And in this video, I'm going to show you how to work with different types of processors. So don't worry about it. And here, the last component is exporter. It means that we send the final trace data to where you want to store or view it. Okay, a tracing backend. And in this video, I'm gonna use Grafana Tempo as our tracing backend. If you have multiple exporters, you can send the final trace data to multiple exporters at once through fanout. Okay, so we receive our trace data. We send it to the first processor. It processes the trace data. It goes to the second processor and so on. And we have the last processor here, and the last processor send the trace data to the exporter, a tracing backend like Grafana Tempo. And we're going to implement this tracing pipeline in this video. But now we're going to show you a demo application, okay? For this video, we need a tracing demo application to just show you how to work with auto-instrumentation, manual instrumentation, how to receive our traces, how to process them, and how to send the traces of our application to a tracing backend like Grafana Tempo. Therefore, we need a demo application for this video. Because of that, we built a small online shop using microservices. This is a very simple application, and it's made of 3 services, each with a clear job, okay? But before diving deeper into its source code, I want to connect to this app through the web browser to just show you how it works, and then we will dive deeper into its source code as well. So its URL is my server local, and this is the node port of my application because I deployed my application in the Kubernetes cluster, and I'm using node port for the application service. Okay, to connect to this application. This is just a demo, but you can use Ingress if you want. But I'm using node port for the demo. I click on it, and yeah, this is the front end of my simple application. In the left side, we have 3 different types of products like Alloy t-shirt, Tempo mug, Grafana sticker pack. And you can simply add these products to your shopping cart. You can remove them if you want. And this is a single application. This application has 3 different important services like cart service, product catalog service, and store front-end service. For example, product catalog service, it stores and lists products that users can browse. For example, it lists 3 different types of products here. Cart service is it manages shopping cart actions in this application, like adding or removing items. Okay, and a store front end, the website users interact with, and it connects to the cart and product services behind the scenes. Okay. To monitor this app and understand how it behaves, we added tracing using OpenTelemetry. So now let's look at how we instrumented each service, either automatically or manually, and how spans and traces are created in our code. In this application, I'm using both manual and auto instrumentation. So now let's go to see the source code of our application. So the first service here is cart-service, and it has an important file called main.py. This service exposes 3 different endpoints to view cart items, to add item to cart, to remove item from cart, and it stores cart data in memory. It has no database, okay? But the most important thing is that we didn't add any custom tracing code here for this specific service. But when we run this service, I mean cart service, with the OpenTelemetry Kubernetes operator, it will automatically instrument this service because we deployed this application in our Kubernetes cluster, and we can use OpenTelemetry Kubernetes operator here as well. Okay, so if I type kubectl get pod dash and shop, these are the pods related to our application, and one of these pods are related to cart dash service. Okay, so we can add instrumentation points to these specific ports automatically. Okay, and this means that every incoming HTTP request will be recorded as a span. Span data include method, path, duration, and status. So the cart service uses auto instrumentation instead of manual instrumentation to capture basic trace data. Another service here is product catalog service, and it has a single endpoint here called /products, and it returns a list of products from memory. And like the cart service, this has no manual tracing code. Okay, so the OpenTelemetry operator creates a span automatically when /products is called. And that span shows the time it took to return the list, HTTP status code, and any issue if the request fails. So we also rely on auto instrumentation here. It's perfect for simple services. And what about a store front-end service? Um, it is the main user interface of our shop. Okay, it shows product lists and cart on the homepage, lets users add and remove items from cart, and it internally calls the product and cart services. Okay, and this service is actually more complex. So we added manual instrumentation using OpenTelemetry SDK. Okay, and this gives us fine-grained control and help us track key users' action. So let's break it down. Um, as you can see here, we created a manual span with this specific syntax. With tracer.start as current span, the name of the span here is render shop page. This is actually the main span for when someone visits the home page. It shows the total time to prepare the page. And inside this, we create 2 child spans. The first child is fetch underline products, and another child is fetch underline cart. The fetch underline products, it tracks the call to the product catalog service. It records, for example, how many products we fetched and any exceptions if the service failed. And fetch underline cart, it tracks the call to the cart service, and it records how many items are in the cart. Okay, so we have a parent span and we have 2 child span for this specific parent. Okay, another section here is this for actually adding to cart. And we start span when a user adds an item to the cart. We attach product.id, and if the backend fails, we record the error in this specific span. And this helps us understand how often this action is taken and whether it's working properly. And another section for removing from cart, okay? And the name of this span is remove item from cart action. And the same idea, here, but for removing an item. And we add the item ID to the span and log errors if they happen. So this is the code, and we're using both manual instrumentation and automatic instrumentation for our application. So now it's time to work with OpenTelemetry Kubernetes operator. To install OpenTelemetry Kubernetes operator in our cluster, we should go to its GitHub repository. Okay, so I go to this repository, OpenTelemetry operator here. Okay, and it has a very good documentation to show you how to install it in your cluster. But it has a prerequisite. Okay, first of all, you need to install Search Manager as a separate tool in your cluster, and after that, you can deploy this operator. Okay, um, in my use case, Search Manager is available for me if I type kubectl get pod -n Search Manager. You can see that it's now available for me. But if it's not available for you, you can go to this link and install Search Manager in your cluster through kubectl or help. Okay. And after doing that, you can install its operator, OpenTelemetry operator. I copy this command and paste it here. And very good. It deployed different resources for me. And the first one is a namespace, OpenTelemetry operator system. And if I type kubectl get all -n OpenTelemetry operator system, these are all resources related to this operator. Okay, very good. After deploying this operator, some different CRDs will be available for you. The first CRD you can use is OpenTelemetry Collector, which means that you prefer to use OpenTelemetry Collector to collect your traces. But in this video, I'm going to use Grafana Alloy instead of OpenTelemetry Collector, which means that we have our own tracing pipeline and having our own Grafana Alloy configuration. So we don't need this type of configuration because we prefer using Grafana Alloy instead of OpenTelemetry Collector, and we will implement our tracing pipeline. Okay, but another CRD which is very important and we need to deploy it in our cluster is instrumentation. Okay, if you remember, our application includes 3 different services. Okay, um, product catalog service, cart service, and storefront and service. And if you remember, just 2 of them are going to use auto-instrumentation. Okay, so to add auto-instrumentation for these 2 services of our application, we need to deploy instrumentation resource in our cluster. Okay, but the most important thing that you need to install and deploy your instrumentation resource in the namespace that your application is living. Okay, for example, in this case, if our application is in shop namespace, we need to install our instrumentation resource in shop namespace as well. So our instrumentation and our application, both of them, must be in the same namespace, which is very important. Okay. And the instrumentation has a very important argument called Exporter.endpoint, and this is the endpoint of your collector, which can be OpenTelemetry collector or even Grafana Alloy. So in our use case, this will be our Grafana Alloy that we will deploy it in our cluster in a few minutes. Okay, but before that, we need to deploy our instrumentation resource in our cluster. If I go to OTLP directory here, I have a file called instrument.yaml. Here, its kind is instrumentation. Its name is shop-instrumentation to add auto-instrumentation to our own application, to the shop application. And its endpoint is Grafana Alloy. But if you pay attention to my cluster, there is no Alloy instance yet. but it's not important, okay? First of all, we will deploy this instrumentation resource in our cluster, and after a few minutes, I will install and deploy Alloy in our cluster to listen to this specific port to be the endpoint of this instrumentation, okay? So let's first of all deploy this instrumentation resource in our cluster. So I go to tracing course and OTLP directory, and I type kubectl apply-f instrument.yaml-n shop. So if I type kubectl get instrumentation-n shop, yeah, it has been created, and it has the endpoint like this. This is the endpoint of Grafana Alloy, but it's now not available, and we need to install it in our cluster in a few minutes. Okay. And another important thing you need to follow in this documentation is an annotation. Okay. As you can see in our application, we are using Python. Okay. The programming language of our application is Python. So based on our programming language, we need to use an annotation. For example, inject-python equals true. Inject Node.js or Java or even .NET or Go. Okay. We need to add this annotation to the pod to enable injection. Okay, we need to add this annotation to individual pod-spec objects available as part of deployment, stateful set, and other resources. In our use case, I deployed my application through a Helm chart called app-helm directory and templates. This is the Helm chart of our application. For example, cart. One of them is cart, and its kind is deployment. Another one is product catalog and store frontend. And if you pay attention to the pod spec of this deployment, you can see that I used this annotation for all of them. Okay, instrumentation.OpenTelemetry.io/inject-python equals true. I used this annotation for all of them: store frontend, product catalog, and cart-service. And I use inject-python because the programming language of our application is Python, and you can choose one of them based on your programming language. And the most important thing that you need to add it to individual pod-spec objects, which is available as part of deployment, stateful set, and other resources. And deployment is in our use case here. Okay. Very good. So now it's time to install and deploy Grafana Alloy in our cluster to implement and configure our very first tracing pipeline, a basic tracing pipeline. And step by step, we will enhance and we will improve the quality of our tracing pipeline with more components. Okay. But now let's deploy Grafana Alloy to implement our first tracing pipeline. The first thing that is very important for tracing pipeline is a tracing backend, because we're going to send our traces through Grafana Alloy to a tracing backend. And in this video, we're going to use Grafana Tempo as our tracing backend. Okay, therefore we need to deploy it in our Kubernetes cluster. Because of that, I already created a custom values file to override some default values of Grafana Tempo's Helm chart to make it compatible with our use case. Okay, and you can find it in Tempo directory, and it has different options. The first one is related to storage. We need a storage solution. I'm using Minayo. You can use any other storage solutions, but from any other providers if you want. And by default, Grafana Tempo's Helm chart creates a Minayo instance for you. But if you want to use your own Minayo instance or your own storage solution, you can disable it here and provide the data related to your own storage instance here. For example, I provided the bucket name, I also created an access key and secret key in my Minayo instance, and I provided here as well. And this is the endpoint of my Minayo instance, and so on. Okay, so if we get back to the browser and I type my server.local and the Minayo endpoint, the Minayo port, you can see that I already created a bucket here called tempo-traces, and also I created an access key and secret key here, and I provided this data in this file, custom values YAML. And I want my Grafana tempo to be integrated with Minayo. Okay. And another important section here is traces. Based on your tracing protocol, we can enable one of them. For example, Jaeger, Zipkin, OTLP, or OpenTelemetry. And in this video, in this case, I enabled gRPC and HTTP related to OpenTelemetry, and it enables Tempo to ingest OpenTelemetry gRPC and HTTP traces. But you can enable any other providers and any other protocols based on your use case. Okay, very good. So let's get back to the cluster to deploy Tempo in our cluster. The first command you need to type is helm repo add. To add the repository of Grafana using this command, I already did that, so I don't need to add it once again. And after that, you need to go to Tempo directory, and I type helm install Tempo Grafana / Tempo distributed -n Tempo -f custom values and -- create -namespace. And I enter, and very good. So if I type kubectl get pod -n tempo, these are the pods related to Grafana tempo. I need to wait for all pods to be up and running. Okay. Okay, very good. So now, as you can see, all pods in this namespace are now up and running, and it means that Grafana tempo has been connected to my Minayo instance successfully. So very good. So if we get back to Minayo here, and if I click on Object Browser and I click on Tempo-traces, we can see a new file here, tempo _cluster _seed.json. Very good. So another important tool that we need to install is Grafana itself, because we need to visualize our traces, to see our traces. Therefore, here we have a directory called Grafana and Grafana-data sources.yaml, because we need to add the tempo data source to Grafana using this YAML file. And this is the address related to tempo query frontend service in the cluster. And so let's deploy Grafana itself in the cluster as well. And the command here is helm install Grafana, Grafana /Grafana -n Grafana -f, Grafana data sources.yaml, and -- create namespace. Very good. So if I type kubectl get pod -n Grafana, it's now container creating status. So let's wait for it to be up and running. Okay, very good. So now Grafana is now up and running. So now let's connect to Grafana to see it and to make sure that the tempo data source has been added successfully. To access to Grafana, first of all, I type kubectl get svc -n Grafana, and as you can see, its port number is 80, the port number of Grafana service, and you can use ingress to access to this service, or for the demo, I prefer to use kubectl port forward. Okay, and the port number from my host is 8080, and the port number for Grafana service is 80. Okay, so I enter, and I get back to the browser, and here I type my server.local, and the port number is 88. The username is admin, but what about password? To get the password, you need to type kubectl get secret Grafana-and Grafana-o JSON path .data.admin password and pipe it to base 64-D to decode its value. Okay, so I enter and then I copy this value and paste it here. Very good. So first of all, in connections here, I click on data sources. And as you can see, the tempo data source has been added here. I click on it. And to make sure it's working well, I click on save and test. And yeah, successfully connected to tempo data source. When I go to explore, and if you choose tempo here as a data source, and if I click on search, if I click on service name or span name, there are no services and spans here. It means that there are no traces because we have no Alloy instance in our cluster yet. And it's time to install Alloy itself. So let's do that. Here in Alloy directory, there are two important files. Like Grafana tempo, we need to override some default values of Alloy Helm chart to make it compatible with our needs. Okay. Therefore, I prepare a file called alloy-values.yaml, and it has some important options here. The first one is extra ports. Okay. If you deploy Alloy in your cluster without changing its default values, the Grafana Alloy service in the cluster just exposes and uses a single port, which is 1, 2, 3, 4, 5, I think. And it's useful for checking your Alloy configurations in a graphical environment. Okay, but there are two important ports, 4317 and 4318, which are the gRPC and HTTP protobuf ports of OpenTelemetry protocol. And if you want your Alloy instance to listen to these two important ports, you need to define external ports here and then define these two ports under extra ports block. Okay. The OpenTelemetry gRPC port and OpenTelemetry HTTP protobuf port. Okay, it's very important. If you want to integrate your Alloy with OpenTelemetry gRPC and HTTP ports. And another option here is config map. Grafana Alloy Helm chart creates a config map for you by default. But if you want to use your own config map, your own Alloy configuration, you can change it to false, as I did here. And you can point to the name of your Alloy config map, which is alloy-config here. And its key is config.alloy. And the controller type is deployment. Deployment is suitable for trace-only pipelines. And there are many different controller types for Grafana Alloy, like deployment, stateful set, or daemon set. But here I prefer to use deployment because we don't need persistent storage, and it's useful for a trace-only pipeline. Okay. But what about our own config map and our own configuration? There are an important file here called alloy-cm.yaml, which is going to be our Alloy configuration, okay? Our tracing pipeline configuration. As you can see here, the name of the config map is alloy-config, and the key is config.alloy, okay? And this is our very first, very basic tracing pipeline. We just have a single receiver to receive our traces through gRPC and HTTP. And after that, we send those traces to a tracing backend, which is Tempo in this case. Okay. As you can see here, if you pay attention to this configuration, there are no processor components because this is a basic tracing pipeline to just show you how it works, how it behaves. But after deploying this configuration and after seeing our traces in Grafana, I will use different types of processors in our configuration to enhance it, to enhance its quality. Okay, so I'm happy with it because it's a basic tracing pipeline. Okay. Before diving deeper into this configuration and before explaining each of these components, I prefer to deploy Grafana Alloy in our cluster first, and then we will get back here to explain each of them for you. Okay, so don't worry about it. So let's go to our cluster. First of all, we need to apply our config map as our alloy configuration in the cluster. So I type kubectl apply-f alloy config map-n alloy traces. It has been created. So I type helm install alloy grafana /alloy-n alloy traces-f alloy values.yaml. So I enter. Okay, it has been deployed. So if I type kubectl get pod-n alloy traces, I just need to wait for the two containers of this pod to be up and running. So yeah, both of them are now up and running. And then let's see the logs of this pod using this command. And yeah, there is no error here, and it means that everything is okay with our Alloy instance. So now let's analyze our components, okay? And let's start with OpenTelemetry receiver. So to analyze this component, I go to the documentation of Grafana Alloy to show you something. Okay, so in this page related to OTEL call, OpenTelemetry collector, we have different types of components, such as processor components, exporter components, and also receiver components. In our example, we used OTLP, OpenTelemetry receiver, and you can find it here, okay? But you can use other receivers as well, such as Jaeger. For example, if you want to use Jaeger, you need to set it up in the tracing backend like Grafana Tempo to accept the traces from Jaeger. And also you need to set up your Alloy instance to listen to the ports related to Jaeger. And then you can use Jaeger as a receiver in your tracing pipeline. But in this case, I'm using OpenTelemetry receiver because we configured Tempo to accept HTTP and gRPC traces from OpenTelemetry. We configured Grafana Alloy to listen to the ports of OpenTelemetry. Therefore, I'm going to use a Receiver.OTLP here as well. So if I click on it, Grafana Alloy has a very good documentation for each component, such as Receiver.OTLP. In this page, you find out that there are different blocks you can use for Receiver.OTLP, and these are the blocks you can use. For example, output, gRPC, HTTP, and so on. In this case, I just used gRPC, HTTP, and output as three different blocks, but I didn't define any arguments for gRPC and HTTP because I'm happy with their default values. If you want to modify the arguments of each block, you can click on one of them. For example, I click on gRPC block, and it shows a table which are the arguments of this specific block. And you can change the default values of these arguments if you want. But I'm happy with the default values of gRPC blocks and HTTP blocks. For example, gRPC has an argument called endpoint, which its default value is this. And its port is 4317, and I'm happy with this default port because I configured Alloy to listen to this specific port. Okay, so I didn't define any arguments for these two blocks. But for the output, I'm going to send the trace data to a tracing backend, which in this case is Grafana tempo. Okay, so we define an argument for output block. Okay. Another component that we use in our tracing pipeline is OpenTelemetry Exporter, which is used for sending traces to our tracing backend, which is Grafana Tempo here. Okay. The name of the Tempo service that I'm using here is Tempo-Distributor. This is one of the services related to Grafana Tempo. So if we go to our cluster and if I type kubectl get svc-tempo, Tempo-Distributor is one of the services of Grafana Tempo. So I'm using the address of this specific service. And the client block is required for this exporter. So if we go to the documentation of Grafana Alloy once again, I'm looking for Exporter.OTLP. You can use other exporters if you want based on your use case, but I'm using OpenTelemetry Exporter. And it also has different blocks here, such as client, which is required. So we define client here as well. So if I click on it, it shows its arguments. And it has a required argument called endpoint, which defines your tracing backend. And in this case, Grafana Tempo is our tracing backend. So this is the endpoint of this component here. It also has a TLS block. So if I click on client TLS here, it shows the arguments related to TLS block, and you can configure it if you want. But I'm using insecure true and insecure skip verify true for this block. Okay, so to generate and to see traces for our application, we need to generate a new traces here because every interaction error in our application will be recorded as a span. So we need to have some interactions with our application to generate new traces. For example, I add an item to shopping cart, I remove it from cart. So these are interactions, okay? So now if we go back to Grafana and if I click on run query, these are the new traces for our application. So if I click on one of them, yeah, it shows the traces and spans of our applications. These are the spans related to our application. For example, one of them is render shop page. If you remember, we created this span manually, okay? And it belongs to store-front-end service. It shows the duration, start time, child count, kind, status of this specific span. We created this span manually and we didn't define any span attributes for it. Because of that, its span attribute here is empty, but it has some different resource attributes as you can see here. And if you remember, we used auto-instrumentation as well. So, for example, if I click on get/products here, which is an auto-instrumented span, it belongs to product-catalog service instead of a store frontend. It shows the duration, start time, and other information here. As you remember, this is an auto-instrumented span. Because of that, it has some span attributes here. And it also has resource attributes. Okay. When you create a manual span, you can define its attributes as well. But we didn't define span attributes in the code level. but we are able to add span attributes to any type of spans with the processor components in our tracing pipeline. Okay, so don't worry about it. So now it's time to add the first processor component to this tracing pipeline to improve its quality and make it professional. The first processor I'm gonna use is span processor, which is useful for renaming spans, changing their attributes, or even setting the status for the span. For example, you can say that, hey, if the status code of the span is 404, please set its status to error to notify me that there is a problem. Okay, so if you have these goals, you can use this processor. So I'm going to provide two different examples as two different scenarios for you to show you how it works and how to work with it. Okay, so like I said here, there are two different examples. Its type is span and its name is rename HTTP spans. You can change this name if you want. But our goal in this example is renaming a span. We will use an include block here to target only the spans we want to change. And the span we want to change here is get/products. Then the name block here with the from attributes argument will construct a new name from the HTTP method and the HTTP.route attributes, which are automatically added by the instrumentation. Okay. For example, if the value of HTTP method is get, and if the value of HTTP.route is /products, there is a separator between the values of these two attributes. So this span will be changed to something like get /products. Okay. And finally, you send the trace data to another processor, which is set error on 404. But let's go to check another example here. Our goal for this example is that our application might handle a not found case gracefully with an HTTP 404 status code, which is not an error by default, okay? And we want to explicitly mark any span with the HTTP status code 404 as an error for easy filtering in Grafana. Okay, it's very important. So we use an include block here with a strict attribute match to select only spans with the 404 status code. Okay, and also we're using the status block, and the status block applies the error status to this filtered span. Okay, the code here is error, but it can be, for example, okay or unset, but I'm using error here. And it has a description. The resource was not found by the server. So if this span has this value for 4, its status will be changed from unset to error, and we will see this description for this span as well. Okay. And finally, we send the trace data to our tracing backend, which is Grafana Tempo. So I copy its name, Exporter.OTLP, and its name here is Tempo. It means that our last processor is going to send the final trace data to our tracing backend. Okay. And our receiver here, instead of sending the traces directly to the tracing backend, it should send the traces to the first processor. Okay, so instead of sending directly to the tracing backend, I prefer to send traces to the first processor. So I copy it here, I paste it, and its name is rename HTTP spans, and very good. So everything is great, and I've saved the file. And let's go to the cluster to apply it. So I type kubectl apply -f alloy config map the YAML -n alloy traces. And then I type kubectl logs. First of all, let's see the name of the pod. And I type kubectl logs -n alloy traces. And I need to wait for the Grafana Alloy reloader to reload our configuration based on new changes. Okay, our Alloy configuration has been reloaded successfully without any problem. So to generate new traces for our application, we need to have some interactions with it. So for example, I add an item to the cart, I remove it from cart, and these are new interactions and new traces. So I go back to Grafana and I click on Run Query to see new traces here. Okay. So if I click on one of these traces, first of all, I want to show you that, yeah, this span has been changed to get ::/products. If you remember, we use : as the separator here. So we successfully renamed this span from get space /products to get : /products. So we successfully rename it. And another example that we used is setting the status for the spans, which include HTTP status code 404. So to test it, I go back to the application and then I use a wrong path, for example, like this. And I receive a message, not found. So I go back to the Grafana here and I click on Run Query. Okay. So if I click on it, and as you can see here, there is an error icon here, which notify me that there is a problem. Okay. By default, the status of the span is unset, but after applying this processor, set error on 404, the status of this span will be changed to error if its HTTP status code is 404. So for example here, as you can see, its status has been changed to error, and also there is a status message here. Resource was not found by the server. This is exactly the description that we used for our processor. Okay? Resource was not found by the server. So we can see that message here as well. And if I click on Span Attributes, you can see that its status code is 404. Because of that, its status has been changed to error, and also we see that message here as well. So we successfully implemented two different types of scenarios for span processor to rename spans and also setting the status for a span based on a specific condition. Okay. Another processor I'm going to use is Attributes. Okay. Attribute processor is a very powerful tool for adding, removing, or changing attributes on your telemetry data. It's perfect for enriching data, ensuring consistency, and removing sensitive or unnecessary information. Therefore, I'm going to provide two different examples for this component. Okay. Very good. And as you can see here, its type is attribute and its name is add env to frontend. You can change its name if you want. But our goal in the first example is adding static environment attribute, which its value is production, to all spans coming from storefront and service. Because of that, we're using include block to target only the spans of storefront and service. Okay, so we are going to add environment attribute to all spans coming from storefront and service. It means that we won't see this attribute for the spans of product catalog service or even cart service. Okay. And we finally send trace data to another processor component here, which is remove user agent. In the second example, instead of adding an attribute, we are going to remove an attribute. Okay. As you can see here, we didn't define include block here because we're going to apply this action to all spans across all services, including the storefront end, cart service, and product catalog service. Okay. And our goal here is removing http.userAgent attribute from all spans across all services because I think that this attribute is not useful for me and I prefer to remove it. Okay, so the action here is delete, and I'm going to delete it. And this is our last processor in this tracing pipeline. Therefore, I need to send the trace data to our exporter. Okay, so I copy it and paste it here. Its name is Tempo. This is the last processor, so it needs to send the trace data to the tracing backend. And also, set error on 404 is going to send trace data to the next processor, which is add env to frontend. So I copy this processor from here and paste it here. And its name is add env to frontend, and I replace it here. Very good. So now it sends the trace data to the next processor, and the final and the last processor is going to send the final trace data to our tracing backend. So very good. So I save the file, and let's go to the cluster to apply the new configuration. So I type kubectl apply -f alloy config map -n alloy traces. Very good. So I type kubectl logs to see the new logs for Grafana Alloy to make sure that it has been reloaded. Okay. Okay, our alloy configuration has been reloaded successfully. So let's go to our application to generate new spans. So I refresh this page, I add an item, I remove an item as well. And let's go to Grafana. I click on run query. Okay. I click on one of these traces here. Okay. We should check two things. Okay. The first one is environment attribute, which is available for spans of storefront and service. So if I click on one of these spans, which is related to storefront and service, if I click on span attributes, yeah, the new attribute has been added here. Its name is environment and its value is production. But we won't see this attribute for the other spans related to other services. Okay, for example, get/products HTTP is a span related to product catalog service. And if I click on span attributes, we won't see environment attribute here because that attribute was added just for the spans of store front end service. Okay. And another thing was http.userAgent that we removed it from all spans across all services. And as you can see here, we don't see any attribute called http.userAgent. And it means that we successfully removed that attribute from all spans across all services. Okay, very good. So we successfully implemented attribute processor to add an attribute and also remove an attribute. Before explaining the other component, I'm gonna explain that what is the difference between span attribute and resource attributes. For example, if I click on one of your spans, you see two things here: span attributes and resource attributes. But what is the difference between them? Span attribute belongs to a specific span, a single operation or unit of work, okay? And it describes details of that particular operation. For example, it's HTTP method, HTTP route, its duration, and so on, okay? But a resource attribute is different. Uh, it belongs to the entire service, process, or environment producing this span. It provides metadata about where and by whom the spans are generated. For example, if I click on resource attributes here, it shows the metadata like container name, deployment name, namespace name, node name, pod name, and service name, and so on. These are metadata about where and by whom the spans are generated. So it belongs to the entire service, process, or environment producing the spans. So it's very important to know the difference between these two types of attributes. Another processor I'm going to use is Kubernetes attribute, or K8s attribute. This component is essential when running in Kubernetes, as it automatically enriches your traces with valuable metadata about where your application code is running. I'm talking about the resource attributes. Okay. Therefore, I'm going to provide an example for you to show you how to work with this component. Okay. As you can see here, its type is K8s attribute, Kubernetes attribute, and its name is add custom labels. You can change this name if you want. Our goal in this example is adding resource attributes, okay? And we're going to do that through two different ways. The first way is using labels, and another one is metadata. And they are doing this job, I mean, adding resource attributes differently, okay? For example, label is looking for a specific label in the workload of your application. For example, I'm using deployment as the workload for my 3 different microservices, okay? And I'm using a specific label called app for my deployments, like here. App equals to cart service. Its value here is product catalog, and here is app equals to a store frontend. Okay, so we are using this specific label in the deployment of my microservices, and it's going to find this label. For example, app. You can use any other labels that you have in your workload. So okay, so in my case, my label is app. So I'm looking for app as the label, and then the tag name defines the new resource attributes. Okay, it means that it's going to create a new resource attribute called app underline type, which its value will be the value of app label. For example, app underline type equals to store frontend or product catalog or cart service. Okay, so these resource attributes will be added. Okay. And another way to add resource attributes is using metadata. You can find a list of valid metadata in the documentation of this component. Okay. But in this example, I'm just using 3 different resource attributes as metadata here to add them. The metadata like container name, container image name, and pod start time. So after applying this configuration, we will have 4 new resource attributes: app type, K8s container name, container.image name, and K8s pod start type. Okay, so first of all, our components is the last processor component in the tracing pipeline, so it needs to send the final trace data to our tracing backend. So I copy the name of tracing backend from here and paste it. And then I type tempo.input. Okay. And our attribute processor remove user agent needs to send the trace data to the next processor, which is Kata's attribute, instead of sending directly to the tracing backend. So I paste the name here. And very good. So I save the file and let's go to the cluster to apply new changes. So now I type kubectl apply-f alloy config map.yaml -n alloy traces. Okay. And very good. So if I type kubectl logs-n alloy traces, I need to wait for Grafana Alloy reloader to reload my alloy configuration. And very good. Our alloy configuration has been reloaded successfully without any problem. So now let's go to our application to generate new traces. Very good. So I remove an item from cart. So let's go back to Grafana. Okay, I click on one of these traces. For example, randomly, I click on one of these spans like render shop page, which we created it manually. And if I click on resource attributes, yeah, the first resource attributes that has been added here is app_type, and its value here is store frontend. Okay. If you remember, we used a Helm chart for our microservices, and we used a label called app, which its value is the name of the service. For example, cart service, product catalog, or a store frontend service. And a new resource attribute has been added here with this name, app_type. Throw the tag name that we define in our tracing pipeline configuration here, the tag name. App type is the store frontend. And also we added container name, image name, and pod start time. So yeah, container, image name, container name, and I'm looking for pod start time. Yeah, it's here, pod start time. So we added 4 different resource attributes. So now let's go to see another span from other services like product catalog service. And if I click on resource attribute, in this time, instead of a store frontend, the value of app type is product-catalog. And we also see container name, container image name, and pod start time here as well. And it means that we successfully added new resource attributes using this component. Okay. Another processor I'm gonna explain is a filter. Okay, filter is a processor which is very powerful for dropping unwanted traces, logs, or metrics from your pipeline. Okay, it drops data if a condition is true, and you write rules to match the data you want to get rid of. Okay, therefore, I'm going to provide an example for you to just show you how it works. In this example, the type of the processor is filter. Its name is drop catalog service. You can change it if you want. And I'm using a rule here. In this example, our goal is temporarily or permanently stop ingesting traces from our product catalog service. Okay, let's imagine that our product catalog service is very stable and we want to reduce costs by not storing its trace data for a while. Okay, so instead of changing our application's instrumentation, we can simply add a filter to drop all traces originating from that specific service. I'm using service.name resource attributes to apply this condition, to apply this rule. And it means that it drops all traces coming from product catalog service. But you are not limited to just use resource attributes. You can also use span attributes if you want. Okay. So to add a new line, to add a new rule, actually, I copy this line and paste it here. So instead of resource attributes, I want to use span attributes. So I just type attributes here. And for example, an attribute like http dot route equals to slash cart. Okay, it means that it drops all traces that their http.route is slash cart. Okay, so I'm using two different rules for this specific component and processor. Okay, so now this is the last processor, so it needs to send the final trace data to our tracing backend. So I copy the address of tracing backend from here and paste it here. Okay. And our Kubernetes processor needs to send trace data to the next processor, which here is filter. So I copy the address of filter from here. And I copy the name and paste it here. I saved the file. So now let's go to the Kubernetes cluster to apply this configuration. So I type kubectl apply -f alloy config map.yaml -n alloy -traces. Very good. So I just need to wait for the Grafana Alloy reloader to reload our configuration. Okay, it has been reloaded successfully without any problem. So now let's go to our application to generate new traces. For example, I add a card, I add an item to the card, I remove an item from card, and let's go back to Grafana. I click on Run Query, and I click on one of these traces. Okay. And as you can see here, we don't see the spans related to product catalog service. Okay. Because our processor, our filter processor, drops all traces coming from product catalog service. And also, it drops all traces that their http.route is /cart. Okay, so we successfully implemented this processor to drop two different types of traces based on the rules that we wrote here. Okay, very good. Another processor I'm gonna use is transform processor. Okay, um, which is the most powerful and flexible processor in the toolkit. It uses the OpenTelemetry transformation language, or OTel, to let you perform complex modifications that are not possible with the other processors. For example, you can set attributes with this processor based on a specific condition. Okay, or also you can replace the value of an attribute if you want. For example, you have an attribute called password and you want to hide its value. Okay, you want to replace its value with something else. So in this case, you can use a transform processor to help you. So I'm going to provide you an example to show you how it works. Okay, its type is transform and its name is add underline transform. But the most important section here is this. These are the rules I'm using to set the attribute and also replacing the value of an attribute. Okay, so let's analyze and let's explain the first line here. Okay, I'm using set. This is the action. Okay, it means create or update an attribute. And here I'm using attribute http.status class. This is the target attribute. Okay, we are creating a label named http.status underline class, and I'm using 5xx. This is the value we want to assign to our new label. And I'm using where here. This is the condition. The action only runs if this condition is true. But what is our condition? The condition is this. Okay, this condition checks if the value of the existing HTTP status code attribute is 500 or greater. Okay, so if a request results in a server error, this rule add a new label named HTTP.status class equals to 5xx to its trace. Okay. In the next line, instead of 5xx, I'm using 4xx if the HTTP.status code is 400 or greater, and if it's lower than 500. And another one, I'm using 2xx if the HTTP status code is 200 or greater, and if it's lower than 300. Okay. The next line I'm gonna explain is this: a set attribute duration underline ms. The action is to create a new attribute named duration underline ms, and I'm using a mathematical calculation here. Okay, this is a mathematical calculation, and it accesses two built-in timestamps that every trace operation has. Okay, its start and its end time in nanoseconds, and subtract them to find the total duration. Okay, and also, I'm using this number here as well because the result of the subtraction is in nanoseconds, and this divides it by 1 million to convert the final value to milliseconds, which is a more human-readable number. Okay, so this rule calculates how long each operation took in milliseconds and save that value in a new duration underline ms attribute for performance analysis. And the next rule, instead of setting the attribute, we're going to replace the value of an attribute. Okay. And the replace pattern, this is the action. Okay, it finds a text that matches a specific pattern and replace it. Okay. And we're using attributes HTTP, the server name. This is the target attributes to modify. Okay, it contains the name or IP address of the server that handles the request, and also we're using a regular expression here. Okay, a regex, which is special code used for advanced text matching. In simple terms, this specific regex is designed to find a complete server address, like a host name or an IP address or even an optional port number. And we have a replacement value here, 3 different stars. Okay, this is the replacement value. And this rule actually finds the server's full address in the HTTP server name attribute and replace it with this value. Okay, it hides the actual value of server name. For example, if you have an attribute like password, and if you want to hide its actual value, you can use replace pattern to apply your rule to hide it. Okay. Very good. So this is the last processor in our tracing pipeline here. So it needs to send the final trace data to our tracing backend. So from the previous processor, I copied the address of our tracing backend and paste it here. Very good. I prefer to remove our filter processor because I don't want to drop the traces related to product catalog series and so on. So temporarily, I prefer to remove it. Okay, but please make sure that I will provide the full content of this tracing pipeline in our GitHub repository, and you will access to this content. So Don't worry about it, okay? So I remove it from here. And for Kubernetes attributes, it needs to send the traces to the processor instead of filter processor here. It needs to send the traces to transform processor. So I copy its name, add underline transform. Very good, because we removed filter processor from this tracing pipeline to have all traces. Okay, so it's very good. I saved the file, and now let's go to the cluster to apply this configuration. So I type kubectl apply -f alloy config map -alloy traces. Very good. So let's see the logs of our alloy instance, and reloader is going to reload our alloy configuration. Okay, our configuration has been reloaded successfully without any problem. So now let's go to the application here to generate new traces. For example, adding an item and removing it from shopping cart. Okay. And now I go back to Grafana to see the new traces here. I click on one of them. Okay. And randomly I click on one of these traces. And then I click on span attributes. Yeah, we have a new attribute here. Its key is duration underline ms, and its value is this. This is a value in milliseconds. So we successfully added this attribute. Okay. And also another thing is http dot status class, which here is 2xx, because our HTTP status code is 200. So the status class will be 2xx. Okay. For example, if the HTTP status code is 404, the status class will be changed to something like 4xx. Okay. And another thing that we modified is server name. If you remember, we used a replace pattern to replace the actual value of HTTP server name, and we used a replacement value, 3 stars, and we can see the replacement value here. Our goal was hiding the actual value of server name, and we did that through replace pattern. Okay, very good. So now let's go back to our application, and this time I want to use a wrong path to create a new error in our traces, okay, to show you the value of HTTP status class. Okay, so I click on this trace, and there is an error icon here because the status of this span is error. And if I click on this trace, and then if I click on our span attributes, yeah, you can see that HTTP status class in this time is 4xx instead of 2xx, because the HTTP status code is 404. So it's very important to remember that we successfully configured our attributes based on different conditions. And this is the power of transform processor, which is a very powerful component. Okay, very good. The last processor I'm gonna use in this video is batch processor. In simple terms, the batch processor acts like a post office for your application's data, okay? Instead of sending every single piece of data, I mean a trace, individually over the network, which is inefficient, the batch processor collects them first. It puts them into a single large package, I mean a batch, and then sends the whole package or batch at once. This reduces network traffic and improves performance. Okay, this is very important. So I'm going to provide an example for you to know how it works. Its type is batch, and its name here is compression. You can change this name if you want. And there are two important rules here: timeout and send batch size. Okay. The most important thing you need to know that the batch processor sends its package, its batch, as soon as one of these two rules is met, whichever comes first. Okay, this is so important. The first rule here, send batch size. This is the number of items to collect before sending the package, before sending the batch. Okay. If you set, for example, send batch size to 10,000, the processor rule is that once I have collected 10,000 traces, send the package immediately. Okay. And another one is timeout. This is the maximum time to wait before sending the package. Okay. Even it's not full. If you set timeout, for example, to 5 seconds, the processor rule is that if 5 seconds have passed since the last package was send what I have now. Okay, so um, the default value for timeout is 200 milliseconds, and the default value for send batch size is this. Okay, but I'm modifying and I'm changing the default value of these two arguments. And finally, we need to send the final trace data to our tracing backend, which in this case is Grafana Tempo. So the output is correct, but our transform processor needs to send the traces to our next processor, which is batch processor, instead of sending directly to the tracing backend. So I copy the name of the new processor here and paste it here as well. Its name is compression. Very good. So I save the file and let's go to the cluster to apply it. Okay, so now let's apply our configuration using this command, kubectl apply-f alloy-config map.yaml-n alloy traces. It has been configured, so let's see the new logs of our alloy container, alloy instance here. I'm waiting for the reloader to reload our alloy configuration. Okay, our alloy configuration has been reloaded without any problem. So now let's go to our application to generate new traces, for example. And let's go to Grafana. I click on run query multiple times. Yeah, after a delay, our traces will be appeared here. Um, we don't see and receive traces immediately. And the delay we're seeing is the normal behavior of the batch processor. For example, if we generate more traces, like adding an item from shopping cart, removing it from shopping cart, and so on, if I click on run query, yeah, there is a delay here to receive new traces. Yeah. So now we have new traces after a delay. Okay. This delay is normal, is a normal behavior of the batch processor. And the delay is the time the processor spends collecting traces to fill the batch. Okay. Our traces are no longer being sent one by one in real time, and instead they are being held by the processor until either the batch fills up to our sendback size or the timeout is reached, whichever comes first. Okay, and the time it takes for one of these two events to occur is the exact delay we observe before new traces appear in Grafana. Okay, it's very important. For example, if I generate a new trace one another time, if I click on run query, there is a delay to see the new trace here. Okay, the new trace is now here after a delay. So, I think the batch processor can be useful for nearly all pipelines, and I highly recommend you to use it and to configure timeout and send batch size based on your needs and based on your use case. Okay, very good. The last component I'm gonna use is not a processor. This is a connector. Its name is Service Graph. Think of the Service Graph connector as a detective that watches all the traffic or traces between your different microservices. Okay, it doesn't store the full story of every trip, but instead it creates a summary of who talked to whom, how often, and how fast. It takes traces as its input and produces summary metrics as its output. And Grafana then uses these simple metrics to draw the visual service graph map. So as I said, our output is metric. So we need to store our metrics in the backend. And my choice is Grafana Mimir. Okay, so we need to deploy and install Mimir in our cluster. Therefore, I created a directory here called Mimir, and its file here is mimir-values.yaml because I need to override some default values of Mimir's Helm chart. For example, I modified the number of replicas of Mimir's components. I decreased the number of replicas because I'm using Mimir in a test environment, but you don't need to do that for production environment. And one of the most important sections here is that I disabled Minayo here because I don't want Mimir Helm chart to deploy Minayo for me, and I prefer to use my own Minayo instance. Therefore, I'm providing the access key, the bucket name, the endpoint, and the secret access key here. I already created two different buckets in my Minayo instance. The first one is Mimir-ruler, and another one is Mimir-tsdb. And also, I created a secret access key for Grafana Mimir, and I'm using this key in this file. Okay, the secret access key and access key ID here. Okay, so now it's time to deploy Mimir in our cluster using this values file. So I go back to the cluster and I type helm install Mimir Grafana / Mimir distributed -n Mimir -- create namespace -f Mimir values the YAML to override some default values of Mimir's helm chart. Okay, so I enter. Okay, so if I type kubectl get pod -n Mimir, I need to wait for all these pods to be up and running. Okay, so now it's time to add a new data source to Grafana for Grafana Mimir. Okay, Grafana Mimir doesn't have a built-in data source in Grafana, and we need to use Prometheus data source for it. Okay, so I go to Grafana data sources here, and I add it. Very good. Its name is Mimir, but its type is Prometheus because it doesn't have a built-in data source in Grafana. But the URL is the Nginx service, which is available in Mimir namespace, because when you install Mimir through its Helm chart, it deploys Nginx for you as well. Okay, so you can use it here. And another data source is Tempo, and everything is good. But the most important thing here is making a link between these two data sources. Okay, it's very important. So I added here JSON data to Tempo data source. The service map data source UID Mimir. This field is a pointer that tells Grafana where to find the service graph metrics. Okay, it instructs the tempo data source to query the data source with the UID Mimir when rendering the service map visualization. It's very important. Okay, so I save the file and let's go to the cluster to update our Grafana instance. I type Helm upgrade Grafana here, and the name of the file Grafana data source is the YAML. I enter. Very good. It has been updated. So I type kubectl get pod -n Grafana. I just need to wait for the new pod to be up and running. Okay, very good. It's now up and running. So now let's go to Grafana here, and I just need to type the username and the password. The password is this. I copy it and paste it here. If I go to data sources here, Grafana Mimir has been added, but its type is Prometheus. Okay. And if I click on save and test, yeah, successfully queried to Prometheus API here. And if I go to explore for tempo data source, I click on service graph here. It shows a message. No service graph data found. Please ensure that service graph metrics are set up correctly according to the tempo documentation. So now it's time to add our service graph connector as a new component to our tracing pipeline to have a new data in this page. Okay. So now let's go to do that. Okay, I provide a configuration here. We have 3 new components here, okay? This configuration creates a pipeline that transforms traces into service graph metrics and sends them to Mimir, okay? The first component here is service graph connector. This is the first step. It receives traces data from our application, and it analyzes the traces and generates new metrics based on the service calls it sees. Okay, it then pushes these newly created metrics to its output. The output is Prometheus exporter here. Okay, this component acts as a middleman. It receives the metrics from the service graph connector and formats them correctly to be sent to a Prometheus compatible system. It then forwards them to the next step, which is Prometheus remote write here. Okay. This is the final step. It takes the formatted metrics and actively pushes them over the network to the URL provided, which is our Mimir instance. Okay. So the most important thing you need to remember from Service Graph Connector is that its input is trace and its output is metric. Okay. So we need to send traces to this component. Because of that, our first component in this tracing pipeline is OpenTelemetry receiver, which is sending traces to the first processor. And now I'm going to add a new output for this receiver, which is the address of service graph connector. So I copy the name from here. Okay. Dot basic dot input. Okay. So our OpenTelemetry receiver is going to send traces to 2 different components. The first processor and also our service graph connector. Okay, very good. So I save the file and now let's go to the cluster to apply it. Okay, so I type kubectl apply -f alloy config map.yaml-n alloy traces. And I type kubectl logs to see the new logs of our alloy instance. And I'm waiting for the reloader to reload our configuration. Um, but before going to the next step, I want to show you something here, okay? Um, our service graph connector has an important argument called dimensions, okay? And its value here is http.method, which is a span attribute. You can use any other attributes you want. But for this case, I'm using this attribute, http.method. But what is this? Um, Dimensions are attributes from your traces that are added as labels to the outgoing service graph metrics. Okay, and this enables you to group and filter your service map data with greater detail for deeper analysis. Okay, and here I'm using a http.method, which means that it lets us analyze performance based on the specific action, like separating get from post requests, separating read from write requests. Okay, so I will show you this label when we run a query using PromQL and Grafana. Okay, so don't worry about it. So now I go back to the browser and I want to generate new traces for our application. Okay, so for example, I add an item to the cart, I remove it, and now let's go to Grafana. And here I click on Run Query. You won't see the service map and the service graph map here immediately, and it takes some time to see it here. So I pause the video and I will get back here. Okay, now we are able to see the node graph here, the service graph map. And one of the most interesting thing about it is that it understands the relationship between the different services of our application. For example, there is a user who is working with the storefront end, and our storefront end service is calling two other services in our application. The services like product catalog service and cart service. Okay, so we can see the relationship here. It's very interesting. So, so now instead of tempo, I click on Mimir data source to show you something. I want to run a query. The query is this, traces service graph request total to get the total requests in our application. Okay. And then I click on run query. And we can see the number of requests from, for example, storefront end to cart service, or the number of requests from a storefront end to product catalog service, because a storefront end needs to call other services. And also, we separated get requests from post request, read request from write request using http.method attribute. If you remember from our tracing pipeline, we use a dimension here in our service graph connector called http.method as the attribute. And we can use this, we can see this attribute as a label here as well, http.method. But service graph adds client to it. For example, it's client HTTP method. And here it's server HTTP.method. Okay, so it adds client and server to this label. Client HTTP method and server HTTP method. But the most important thing is that we separated the read and write requests from each other using this label. You can use other attributes if you want. Okay, there is no limitation, but I just use http.method. And it's important to understand the relationship between client and server in service graph. Okay, um, think of any request between two services as a phone call. Okay, a client represents the action of making the call, and server represents the action of answering the call. Okay, and the entire job of the service graph connector is to find these matching pairs of phone calls. Okay, it finds the client span in one service and link it to corresponding server span in another. Okay, the successful pairing creates a single edge on the service map. Okay, so it's very important. So I think we covered all related components in our tracing pipeline. For example, I explained receiver, exporter, and also a list of processors. And also we learned how to work with service graph connector as well. So thank you very much for watching. I hope you like it and see you soon.